Okay, so we're going to start today with some more amplifier frequency analysis. So what we did last time is kind of look at the frequency analysis tools. And there was sort of three tools that we used. One was Miller, an approximation, zero circuit time constant, short circuit time constant. So these are kind of the three that we said in different scenarios would be better or more appropriate to use. And today we're going to look at several more sort of single transistor and cascades of amplifier configurations so that you can build up a little bit more intuition how to analyze these resistances seen by different capacitors in the circuit, things like that. So we did common source last time, and now we're going to move into, let's say, common gate. If you look at that topology, we have something that's like a load resistor, and then we'll have our source resistor and, let's say, the voltage in here. And I'm grounding this because I'm just showing sort of the small circuit analysis. This would also be grounded in that case. And there's really two capacitors to consider here. So one is going to be CGS. And then we'll see that CGD, which we looked at last time, is actually not playing as much of a role here, but we'll still consider it right now before we kind of discard it. So for this type of topology, if we draw this sort of the small signal model, what you get is CGD goes to ground. There's also a CGS here. And we have GM. I'll also make this guy kind of grounded here. So, well, for ease of analysis, let's assume this is actually connected here. So I don't have to worry about this. And then here I have my RD, and that is grounded. Okay, so if we look at this, I could go and look at the number of capacitors and essentially say, okay, well, it's two capacitors, there's no loop, so it's roughly two poles. Okay? And there's no direct capacitor on the circuit path, so from input to output, so there's no zero. Right? And then I can go and sort of analyze it using open circuit and short circuit time constants and try to figure out both of these. And so that's what we're going to do. But let's first do sort of the exact analysis just so we know what we're going to be dealing with. So if you take a look at this, I can just use my kind of voltage divider or cascade techniques, and I can write that V out over V in is the first thing it's going to be a voltage divider between this RS and whatever the input impedance I'm seeing in this node. So in this case, 1 over SCGS is just some impedance that we're seeing. So what we're going to see, instead of just seeing 1 over GM, now we're seeing 1 over GM in parallel with that 1 over SCGS. So it's really 1 over GM plus SCGS over RS plus the same thing. Right, so that's the first voltage divider. And then we have sort of our standard GM times whatever the output impedance is, so that's the gain. But in this case, it's not just RD, it's a parallel connection of RD and 1 over SCGD. I can write out this part as sort of RD over 1 plus SC GDRD. Right? And so if I do that and I multiply this out, what I'm going to be getting is GM and RD from here times, and then from here I'm going to have 1 over RS times GM plus SCGS plus 1. And then I'm going to have this piece over here, SCGDRD. And then this piece is 1 plus RS GM plus SCGS RS. So I can take this piece out and get GM RD over 1 plus GM RS. This should be familiar because this is our DC gain, right? Times, and then what I have here is 1 plus SCGS RS over 1 plus GM RS. And then times another term, which is 1 plus SCGDRD. So if you take a look at this, this is our A0. And then these two are the two poles that we have in the system. So, so this will be 1 over 1 minus S over P1, and then 1 over 1 minus S over P2. Right, so from here we can extract the magnitude of the pole as 1 plus GMRS over CGSRS, and the second one is 1 over CGDRD, right? So this is kind of the exact expression. Now, it's a bit tedious, so if we go and take a look at how we can do it with open circuit or zero circuit, zero value time constant. We can say that if you take a look at the circuit again, it's from CGS perspective, there is RS here, and then so what our pole 1 is going to be, if we apply OCTC, then we're getting a dominant pole. So it's going to be 1 over, and then the sum of, from different capacitances. We're going to have something from CGD, plus we're going to have a contribution from CGS 0. So if we're looking from CGS, then sort of this is the equivalent circuit for RGS 0. Right. And what we have here is that RGS 0 is equal to RS in parallel with 1 over GM. And then RGD is simpler. So RGD would really be what this capacitor sees, but that's only RD. So your pole would be minus 1 over CGDRD plus CGS times RS in parallel with 1 over GM. And so if we go and take a look at the other pole. So for the other pole, we're going to be using, so for pole 2, we're going to use short circuit time constant, because we know there's 2 poles in the system. If one is dominant, so it's much lower magnitude, I can use short circuit time constant to identify the largest pole, largest magnitude pole, and that has to be P2. So we're going to use short circuit time constant. And so in that case, P2 will be minus 1 over CGD times RGD short, plus 1 over CGS times RGS short. And then just to take a look at these RGD. So RGD short is again RD. And RGS short from here, that would also be kind of the same thing in this case, simply because whether I've shorted CGD, it makes no impact on okay, sorry, I don't know what this is. Makes no impact, whether I've shorted the CGD or not, makes really no impact on what this source is seeing. So it's still seeing RS in parallel with this thing over here. Okay? So it's still going to be RS in parallel with 1 over GM. So now we have P2 is minus 1 over CGDRD plus 1 over CGS, in this case RS in parallel with 1 over GM. So now taking a look at this expression and this, we can start making some assumptions. Right? So if I look at this term in particular, if RS is larger than 1 over GM, this piece over here is approximately omega t. We know omega t is really large, right? So if omega t is really large, then 1 over omega t, which will be this piece over here, is going to be really small. So that piece is not going to be a dominant time constant. And because it's not a dominant time constant, then then P1 will be really 1 over CGDRD, because this is going to be the dominant piece. Okay? And if it's dominant piece because CGDRD is big, then 1 over CGDRD is very small. So this is not a dominant contributor to this whole sum. So then P1, and this is dominant, and then P2 will be minus 1 over CGS, or minus GM over CGS, which is approximately minus omega t. Does that make sense? So one of the things to note here is that this pole 1 doesn't have any Miller multipliers. If you recall from the last lecture, there was essentially a GM times RS term multiplying this RD when we talked about the, so in terms of the P1, let's say, common source, that was approximately 1 over CGD, and then here GM RS RD. Right? So there was this multiply, and some other terms, RS, RD, etc. So this was because of the Miller effect that we're sort of multiplying out this time constant. And so that would have been sort of a more dominant pole than this one over here. Okay. So these amplifiers, sort of common gate amplifiers, are much wider bandwidth than in the case of a common source. Okay, so let's take a look at the other type that also will end up being kind of a very wide band. And of course, you want it because it's not really providing any gain, so it's just isolation. So in this case, it's the common drain. So if we do VI, and then we have RS, and then RL here and V out. And we can sort of, actually, let me just, I'll draw it here just so that it's more compact. Now, in this case, I'll sort of ground this just because there's an easy way for me to lump this effect in. So when I do the small signal, I have the RS, and then here, and then from here, and then notice that I can do here, so this is V out. I can do here GMB V out. But with this, since V out is really here, and so V out is also kind of powering this current, this is equivalent to having some RL prime here, which is equal to RL in parallel with 1 GMB. Right. Because if I have a voltage drop of V naught over a current source that is GMB V naught, then the transmittance is GMB. Okay. So we're going to be essentially lumping this effect right into this RL prime, and then we don't have to worry about that branch. So the reason why here I'm not going to do immediately zero open circuit time constant or zero value time constant is because I do have this CGS directly on my path, okay? And it's a rather large capacitance. So I'm guessing there will be a zero there that's actually pretty important, okay? So, or at least that, yes? So I neglected it, okay? And you'll see, so CGD is, well, it will be here, of course, right? But this is terminated to ground. So this is not really kind of, the signal is not really going through CGD in order to get to the output. It is true that CGD is kind of loading this node, but so is CGS, which is normally much, much bigger, right? And so the assumption is, in the end of the day, CGS is going to dominate whatever behavior is there. So I'm just not including it. Okay, but if you want a more tedious derivation, you can kind of include it and see later that it doesn't really matter. So this is one of the advantages of and so this is actually a really good question that's also related to the homework, is that in some cases, CGD will be important. And that's usually when you're having configurations like common source where you have to take into account the Miller effect, right? So then that CGD, even though not that significant, will get multiplied up by whatever the gain of that transistor is, right? So in these configurations, you don't want to ignore CGD. But in these, and as well as we've seen in common gate, it's sort of, in common gate, you don't ignore it, but it's easier to calculate. And you'll see that it sort of, it does affect your pole, but your pole is very, very far away, right? Or much further away than in the common source amplifier. But here, it's really not on the path. So you can also ignore it. So let's get back to this CGS, because that is really an important capacitor. And just looking at this, you sort of see that, okay, if frequency is very large, this CGS will be a short, right? But this CGS is used to develop my VGS voltage, right? So at very high frequency, if CGS is a short, it's actually giving me 0 VGS here, right? So that's where sort of the zero behavior is coming from. Okay. And then really my VO is just like VIN almost, right? It's just a voltage divider between RS and RL prime. Okay. So let's write it out a little bit here. We can't use the approximations because approximations don't tell us anything about this zero. We can at best calculate both two poles for CGS and CGD. In this case, I just have one pole because I'm assuming there's CGS. So I need to do a little bit of the exact analysis here to figure out what this zero is. So what we're going to say is that V out is RL prime times whatever current flows into it. And that will be this I in plus GM times VGS. And again, VGS is developed on CGS, so it's I in over SCGS. And so I can write it as RL prime 1 plus GM over SCGS and times I in. Okay. And then we can just 1 plus GM over SCGS. And then we can sort of write out what the I in is, which is VI minus V out, and then divided by the series impedance of RS as SCGS. Again, from here we can now sort of have a V out V in relationship, right, with a little bit of algebra. So if we move this to the other side, we get RL prime, and then here SCGS plus GM over SCGS RS plus 1. I'm just multiplying this out so it's easier. And that equals RL prime times SCGS plus GM over SCGS RS plus 1 times Vn. And so when we divide this out, I'm going to get RL prime times GM plus SCGS over 1 plus SCGS plus SCGS RL, and then plus GM, RL prime. And now we can kind of pull things out so we get a familiar expression, which is the DC gain plus, so I can pull out GM from here and 1 plus GM RL from the bottom. And we're going to get GM RL prime over 1 plus GM RL prime times, and then what's going to be left, the numerator is 1 plus SCGS over GM. And then here, 1 plus SCGS. Sorry, I missed RS here. And then we have RS plus RL prime divided by 1 plus GM RL prime. So again, this expression is kind of our A0 times 1 minus S over Z1 over 1 minus S over P1. So we can sort of match 0 and pole. Right. And so from here, 0, 1 is minus GM over CGS. And P1 is minus 1 plus GM RL prime over CGS RS plus RL prime. So we can then do a little bit of an analysis here. So let me just put it on the other, so it's a little bit clear. CGS, and then P1 is minus 1 plus GM RL prime over CGS RS plus RL prime. So if we assume that GM RL prime is sort of much bigger than 1, and we have also that RS is a bit smaller than sort of RL prime, which is sort of typical. Your input source impedance will supposed to be low. Your load is supposed to be high, right? So you can get some gain. Then, of course, this term is going to be dominant, so RL prime is going to cancel out. So this is approximately then going to be P1 is again, something like minus GM over CGS, right? Because RS is much smaller than RL prime, so this is going to dominate. Then these two will cancel out, and GM will stay. And so this is kind of in the ballpark of our 0, 1. So it's basically, in typical scenarios, pole and 0 will be pretty close to one another, and like they're around, both will be, if CGS is much bigger than CGD, etc., then obviously both 0, 1 and pole 1 will be approximately minus omega t, right? Which means that this is a pretty wide band amplifier, right? Its bandwidth extends all the way to omega t. Of course, it has no gain, right? So that's why. And usually you'll see that sort of the gain bandwidth kind of in these amplifiers stay constant. So you're trading DC gain for bandwidth. The higher the DC gain, the lower the bandwidth, et cetera, right? Okay. So just to complete, sort of, if you looked at the book, we've sort of skipped the full analysis for the common source because it's a little bit involved. It will take a little bit of time in the lecture. So, but I just did the poles, pole 1 and pole 2. But since the transistor has this CGD that goes to the output, of course there is a 0 there as well because it sort of bridges the input to the output, right? And so the magnitude of that 0 is, okay, it's actually, okay, I don't know what's going on. It's actually of this form, and it's actually a right half plane 0, so it's not a negative sign there. And although this is very small, it will play a role when we start doing the stability analysis. So once we get into kind of this, now we're just doing the frequency response, but once we get into the stability analysis of like multi-stage amplifiers, you'll see that this feed-forward 0 would essentially have a bit of a role. So we've done kind of the exact thing here for the common drain. And that was just to identify essentially this 0, but we can still use the techniques that we talked about earlier, like ZCTC, to identify the dominant pole. So for that, you have a circuit where you have your RS, and then you have VT, IT, and then I'm just going to simplify it as GMVT because VT is now VGS. And then here we have RL prime. So the current that flows through here is obviously, so we can do it like, this current is GM VT minus IT, right? So when we write it out for this voltage, we're going to have RL prime, which is the resistor here. So we're going to do this voltage first, which is the V out. This is the current that flows through this, plus VT will be equal to the voltage developed on RS. So then we have 1 plus GMRL times VT, RL prime, equals RS plus RL prime times IT. So our RGS open circuit is then RS plus RL prime over 1 plus GM RL prime. And so this should be sort of a familiar expression from the previous exact derivation. And then we have another term which is, in this case, I could afford to sort of look at what CGD impact is as well because it's easy, right? So I could say, oh, okay, well, if there was CGD, I would have kind of RS, and then I would have a CGD here, and then open here, and then so this branch doesn't matter because it's all originating at 0. If I replace this with VT, I only see RS, right? So I can say that RGD 0 is just RS. Okay. So my pole will be equal to minus 1 over CGS RGS 0 plus CGD RGD 0. And that's minus 1 over GS RS plus RL prime over 1 plus GMRL plus CGD times RS. Now, both RS and CGD should be small values. So therefore, this piece will definitely dominate. Okay. So that's why we can kind of neglect this part. And then we get kind of the expression that is very close to our exact pole 1 that we had in the system, in the previous analysis. Okay. So just to complete sort of the portfolio of devices, we haven't really looked at bipolars, but for common collector, it would be something very, very similar. And in the book, you sort of have this generalized example with Rin and R load, so you can kind of just plug the values in. But for the common collector, you would also have the feed-forward 0 from CPi, right? Because that bridges the base to the emitter. And so you would get something like over CPi, which again is kind of approximately minus GM over CPi, and that's of course minus omega t. And then for the pole, you would get something like R pi in parallel, and then have very similar expression to what we have up there for CMOS. Now, of course, the only difference is that now we have R pi in parallel with this, because R pi sort of bridges the CPi resistor. So it has to be kind of in parallel with whatever CPi's resistance is seeing. Right? Now, with all of these, I mean, it's so if, you know, even in this case, sort of this one again is close to omega t, right? So both common collector and common drain amplifiers will have a very large bandwidth. And that's kind of the bottom line that you should remember. Okay, so there is another kind of interesting property of common drain amplifiers or the topologies where you're kind of looking at the impedance at the emitter or the source up, sort of as the output impedance. We'll see that we can use that later in active loads and things like that. But that impedance can look inductive sometimes because there's like 1 plus S, CG, S, RS. So you can modify that resistor in the gate. But if I have time, I'll go through that. If not, it's kind of nicely described in Chapter 7, so you can take a look. But I want to sort of focus on the multi-stage amplifiers just to give you a little bit more ammunition for homework. So I mean, there's really no magic bullet. We've learned these tools, so you just have to kind of go through them. But there are some certain circuit topologies that you're going to encounter much more frequently in these kind of multi-stage things. And if you know the solution for that, then it's kind of easier to pattern match. So let me show you an example here. If we use Cascode, normally, okay, that's our RD, and then we go into one FET and another FET, and then this is our RS V in. And I'll assume this is just, you know, for small signal, both of these are kind of at ground. And I'm just now looking at kind of the influences of different capacitances, right? So I'm going to have CGS here that's trying to short this gate. So obviously, it's going to be some sort of a pull involved because it's trying to kill the signal coming in. I have a CGD, which is going to try to kind of forward the signal. But also, I'm looking, we learned that in common source, this CGD will have a Miller effect. So it will be showing up here as some like higher capacitor, right, by whatever the intrinsic gain, the gain of this M1 is. And then again, at the top, I have the CGS of this guy and its own CGD, right? Okay. So if we look at the V out versus V in, at DC, it's minus GM1 times RD to the first order, right? Because we said that the first stage is GM1 times whatever it sees up here, and what's seeing up here is 1 over GM2. And then the next stage is GM2 times RD, right? So this is because it was minus GM1 times 1 over GM2, and then times GM2 times RD. So these two would get cut. This is approximate. I'm not considering GMB or anything like that. It's the most dominant effect. So if we label this node X, that means that Vx over V gate is exactly that, minus GM1 over GM2. Now, if these transistors are roughly the same size and same currents flowing through them, with VGS voltages being kind of the same, minus VT, that this is approximately going to be minus 1. So it's not going to be a lot of difference between these two GMs. And notice that this is your Miller multiplier. So what this means is this first stage doesn't really behave like our common source amplifier in the normal topologies, because its gain is actually, its voltage gain is very small. It's approximately 1, right? But it's just transducing voltage to current so that this common gate stage can actually do all the amplification, okay? And we know from the common gate analysis at the beginning of the lecture that common gate amplifier is actually a lot wider bandwidth. So what I'm doing intuitively here, I'm improving this input bandwidth simply because I'm killing the Miller effect. So my CGD is not as big as if I was basing all the gain of the amplifier on this stage over here, right? So I'm improving the input bandwidth. And then also, at the exit, I'm using, in the second stage, I'm using the amplifier that inherently has a much wider bandwidth, which is the common gate. So that's sort of the benefit or the beauty of the cascade amplifier, right? By cascading these two and not having the voltage gain in the first stage, I improve the input bandwidth, and then I also improve the output bandwidth. Okay, so if we go and kind of look at the dominant pole for this, we can obviously use zero value time constant analysis. And I can go and immediately write out what that is. But before I do that, I just want to kind of show you one circuit here and how to solve it, because it's actually a very useful circuit. And so I'm going to apply VT between these 2 points, and there will be IT as a test current here. This is a typical configuration for when CGD wants to see what the resistance is around. You're going to usually see these topologies, because this RA will be some RS on this side. This RB will be whatever is the resistance that you see up the chain, or whatever the input resistance is from the next stage in parallel with your own output resistance, right? And then this is usually going to be your transistor current. And so this is kind of a nasty circuit to just go and write out the Rin. But if you kind of remember what the Rin is for this type of topology, it will be very easy for you to go and just crank out the analysis. And so let's just go through the pain of kind of doing it once, and then you can see what it is. So VA is RA times IT, and then so I'll have RA times IT, that's this voltage, minus the V test, equals this voltage developed on RB. So it will be minus RB times GM RA I test, that's my VA, and then plus I test. So this is because this current is negative sum of these two currents. Okay, and from this I can sort of move all the things on one side and have RA plus RB plus GM RA RB equal V test over I test. Okay. So it's kind of funny if you take a look at it. What this current source is doing, it's kind of multiplying up these two, the product of these two capacitors, right? Oh, sorry, resistors. And so you have RA on one side, RB, but it's like adding in series another product, GM-RA RB. So that's going to be kind of your typical Rin looking from this side. So whenever you have a CGD in the circuit, that's kind of the open circuit time constant that CGD is going to see. So then we can go and just write this out. So the pole will be 1 over, let's say, CGS1. So that's this one. And this one will just see RS, right? And then CGD1. And then we said it's seeing some combo like this. So that combo is going to be RS plus RB is really whatever we see on this side over here. And that is what? If we forget R naught, what do we see on Vx? 1 over GM2, right? That's right. And then, sorry, because there's this multiplier, we see GM1 over GM2 times RS. Right, that's this combo over here. And then plus, I'm just going to continue. Then I see CGS2 times, so CGS2 only sees the input impedance of the M2, which is 1 over GM2. And then I have also CGD2 over here, which sees just RD. Okay. So if you take a look at all this, so compare to common source, where you have that P1, okay, this is negative, okay. 1 over, and we had RS CGS plus CGD times RS plus RD plus GM RS RD. Okay? So this is the key point that, so this term is kind of constant, but I have CGD times this term over here, right? So there is RS in both, but this CGD gets multiplied by the GMRD, which is the gain of that stage. So that's the Miller effect. Okay? And that's why this now becomes not insignificant, right? Because then I'm comparing my CGS to CGD multiplied by the gain of the amplifier. So if one higher gain, that input bandwidth is going to be very limited. Now here, I don't have any of that, because here, I just have RS, because these two are pretty similar. This is my Miller, right? So it's very small. And then at the output, again, I have CGD times RD. So there's no multiplier. But my intrinsic gain is GMRD, right? So I've sort of decoupled a little bit gain from the bandwidth in this case. Yeah?
So would you get the same answer if you first decoupled your capacitances?
With Miller effect, you would yes, you would basically get kind of this thing with this thing over here, right? You would still not have to account for this piece, right? So I can kind of combine Miller effect with zero value time constant analysis. These are two effects that can be done. Yeah, this has been like the whole 2 days on all cell phones. Miller effect is something you can combine always with the other methods, because that's just an approximation about the gain between the 2 points, right? But even then, you're going to get sort of now capacitors that are lumped to input, and you're still going to get some capacitors at the output in a multi-stage configuration. You have to analyze kind of the time constants of both, right? Yeah. Okay. So just quickly, I want to give you another topology just so we can cover kind of all the cases you will be able to see in practice. And again, this is very quick because we now have matured beyond kind of drawing out all the small signal models. So I can now do something like this. So let's say this is our two-stage common source, right? And I want to figure out what is the dominant pole for this system. Right? So again, I'm going to say, okay, I'm going to first look at RGSs, and this should be easy. So RGS out, open. Simply because when I'm analyzing RGSs, I'm opening CGD capacitors, right? So I'm breaking that path from input to output, and then it's very easy. So because let's say for this RGS, when I open up the CGD, I only see RS on this side, right? So I can say, okay, RGS1 is RS. RGS2 is what? What do I see from this CGS? This is RL1, this is RL2. RL1, that's right. Okay. Okay, RGDs are a little bit trickier. Okay, so what is RGD1? That's kind of what's seen from this point, right? Okay. Which one? RL1. Yeah, you got it. So this is now bridge, like our pi model configuration, right? We have, again, this situation of RA, and then here a source and RB, right? And then this goes, you know, you're looking from here, right? And this is VA, GM, VA. So same trick, right? And now, what is RGD2? So now I'm looking. Uh-huh. RL1, RL2, right? Okay. So you see where I'm going with this. It's essentially this topology that can help you in kind of a lot of these places. And then in the Cascode, we did the thing of what happens if a common source looks into common gate, for example, right? And so pretty much these are kind of all the topologies you'll be encountering. So you just try to take these shortcuts, okay? And yeah, the homework will kind of reinforce this, especially problem 4, I think. Okay, that's it.